Alright, Assalamualaikum and a very good day to everyone. So today we will continue our next topic, which is regarding on the self-inductance. Alright. So basically, what we're gonna learn in this topic, which is regarding about the, you guys should know about the self-inductance and also how to calculate the inductance. Yeah. So basically, the inductance is denoted as L. So we need to calculate how to get this value of L. And inductor basically is just as capacitor. Okay, if you still remember, capacitor is the one that is stored energy, electrical energy. So for inductor, it is used to store the magnetic energy. Okay, it is used to store the magnetic energy. Yeah. All right. So to know about inductance, you need to know about the flux linkage. Alright. So flux linkage is basically a fundamental concept for a transformer. Okay, it is a fundamental concept for a transformer, and let's in this picture, okay, it is shown to you guys the conventional of transformer. So conventional transformer has a windings. Okay, I think all of you should know about that. So winding is used to ignite the magnetic flux. Okay, so basically at this part is known as the primary winding. Okay, this is known as the primary winding, and okay, and this is known, okay, where is it, my laser? Okay, and this is known as the secondary windings, right? So at the primary windings, they're gonna be current supply, okay, where this current supply will then produce the H field. Okay, so from the H field, of course, the B field, okay, the magnetic flux density will be generated, and from this magnetic flux density, then it will produce the flux. Okay, so this flux will then be transmit, okay, or will be linked, okay, to the next winding, okay, windings, okay, to the next windings, which is at the secondary winding, okay, and via the transformer core. Okay, so this is the transformer core. So from the H field that is produced by the value of the current of I supply, okay, the permeability of the materials of the transformer core will then affects the value of B that will be produced. Okay, so due to the applications of I1, the flux will be produced. Okay, how the flux will gonna be produced, as I mentioned, it will generate the H. From the H, it will generate B, and from B, it will generate the flux. Okay, so the flux will be linkage to the secondary winding via the transformer core, and this flux linkage will generate the current. Okay, at the secondary windings, it will generate the current, okay, where this current is called as induced EMF current, okay, at the secondary windings. Alright guys, so now let's look what is self-inductance. So self-inductance is the origin of inductance. Okay, it based on the flux linkage, right? And we consider a toroid structure of a coil. Okay, so this is a toroid structure. Okay, it has n number of turns, okay, at coil 1, and there is a supplied current of I1 is being supplied, okay, at the primary windings. Okay, and of course, when I1 is supplied, it will then generate the H field, and from the H field, it will generate the B field, and from the B field, it will then generate the flux. Yeah? So the magnetic flux in the toroid's core is proportional to the I1, and if we can write in terms of proportionality, okay, the value of I1, which is the current, okay, is proportionate, yeah, to the value of number of turns multiplied with the flux. Okay, so meaning that the higher the value of I1, more flux will be produced. So if you want to write this in terms of equation, okay, general mathematical equation, of course we need to introduce one constant, one what we call it as mathematical constant, right? So it will be N1 flux at 1, okay, at the primary side is equals to L1, the inductance at the primary side, multiply with the I1, right? So therefore, if we want to find, okay, this L is known as inductance, okay, is known as inductance. And if you want to find the value of L1, it can be written as N1 flux 1 multiplied with the value of I. Alright. So L is called as L1, is called as self-inductance. It produces their own inductance. Okay, it produces its own inductance based on the currents that is supplied to that part. Alright. So the inductance is the unit of inductance is written as Henry. Okay, which is symbol as H. So L1 is equals to N1, the number of turns multiplied with the number of flux divided with the number of current supplied. Okay, so alternatively, there is another way to find the flux. So this is the first method to find flux. There is another method to find flux, which is by using the magnetic energy comparison. Okay, so magnetic energy, we know from previously lecture, magnetic energy can be calculated by using the half of integrations b dot h dv, right? Magnetic energy also can be calculated by using the number of inductor and current, which is Wm, which is the energy here, is equals to half the number of inductor, the number of inductance supplied, multiply with the current, square of current. So if we compare both of this, okay, it can be write as such. Okay, is equals to a half Li squared is equals to half integrations of BH dV. So then, in order to, if we want to determine the value of L, it can be written as L is equals to integrations B dot H dV divided with I squared. Okay, so there are two methods, alright? There are two methods. One, you can use this, and another one, you can use this formula. So it depends which formula you want to use. You need to look at what kind of informations that you have. Let's say the flux is given to you, then you can straight away use this equation, right? Okay, now let's look at example number 1 for the self-inductance. Okay, the structure that produce its own inductor. So there are two long straight cylindrical conductors, each of radius a, are separated by the distance d, and the conductors are used as go and return circuit. So find the total inductance per unit length for that particular structure. So there are two straight cylindrical conductors. Okay, the radius is given as a, both of them a, and this is also a. Okay, and it is separated with this distance of d. So both of this is separated with the distance of d, and it are used as go and return circuit. So meaning that one we're gonna be the directions of the current, one we're going to be on positive z direction, and another one we're going to be on negative z direction. So for positive z directions, it will be going up, right? As such, the current direction we're going to be as such, and another one we're going to be vice versa. Okay. Okay, so once we know the directions of the current, we can estimate or we can determine the directions of the H field by using our left hand side rules, right? So if it is going up, of course the H field we're gonna be on clockwise direction, right? Where if it is the current of gonna be in the negative z direction, Okay, it's gonna be the other way around. You're gonna be on anti-clockwise, right? Anti-clockwise direction. So inductance produced, okay? Inductance produced, we need to consider in two regions, right? So one region will gonna be region that is inside of this conductor, and another one region that is outside of this conductor. All right, outside of this conductor. So there are two regions that we need to consider. Okay, so region number one. Okay, region number one, where your R is lesser than A. So when R is lesser than A, it will produce the H1, yeah? H1. Okay, another one, H1, and from H we can determine B1, and from B we can determine the value of the flux. Okay, so therefore the value of the flux that is produced inside here we're going to be internal flux, right? Because it is inside this particular conductor. All right, and if we know the value of the flux, we can find the inductance, yeah, the inductance at the internal side. Another region we're gonna be at the outside region of the conductors, right? Outside of this, both of this conductor. This conductor is same with this conductor, only the directions of the current is different, right? So what are the range of outside of the conductor? So it must be larger than A. Okay, R must be larger than A, but then it must be outside of this conductor as well. So it must not be larger as D minus A. Okay, A from A until D minus A. Yeah? D minus A for this side. So therefore at region number 2, all the flux is produced is we're gonna be the external flux. Okay, so it will produce H2. From H2 we can determine the B2. From the B2 we can determine the flux at the external part. And once we know L at the flux at the external part, we can find the inductance at the external part. So the total inductance will then inductance at the internal plus with inductance at the external. All right. Okay, so this is our objective, or this is our directions in order to solve this particular solution. I mean this particular questions, right? So let's do one by one. We need to determine the H, B, and flux at the internal. All right. So they didn't mention to us the length of this cylinder. So we assume that it is infinite length. So based on our ACL, okay, for infinite, we can determine the value of H, right? Where this is for R is lesser than A, yeah? We're going to be at the internal side. So H, we're going to be at the internal, but let's just write it as H at region number 1, yeah? H at region number 1, dot dl is equals to I enclosed. So I enclosed, this is based on our previous experience. H will gonna be, H1 we're gonna be at phi direction, right? So dl we're gonna be on 2 pi r. I enclosed we're gonna be, we need to use the proportion, yeah? R squared over the whole area of the currents, the whole area for the cylinder, right? So from here we can find our H1, okay, which is going to be on phi directions. Okay, if we solve, we will get IR 2 pi A squared, alright? Okay, so it must be in a phi directions. So of course from here we can able to determine B and flux linkage, alright? So from here, if we find the B, yeah, the B we're gonna be mu naught IR over 2 pi A squared on phi direction as well, alright? Okay, Before that, guys, okay, in order to find the I at the internal, sorry, not the I, the flux at the internal side. So flux at the internal side, if the area is equals the whole total area at the inside here, the whole total area inside the conductor we're going to be at the area of pi a squared. So at the pi a squared, we can find or we can determine the value of the flux totally at the internal by using B dot ds, where the limit will going to be from 0 until a. So this is the value of the flux that will be produced inside this conductor, where the limit is from 0 until a. So how much the value of the flux we're going to be, if we calculate, so since our B in phi direction, our ds also must be on phi direction, right? So ds on the phi direction, we're going to be dr dz. So if we further solve, we were able to get our flux at the internal side, where the area is at pi a squared, which we're going to be at the total area inside the conductor. We were able to determine the value is mu naught I over 4 pi L, right? So this is the flux that is generated by pi a squared area inside the conductor. Okay, but now the one that we want or we wish in this region, when your R is lesser than A. Okay, when our R is lesser than A, so same as the current that we have solved before, where we use proportion. So same goes with the flux. We also need to use the proportion. So for the area of pi r squared, okay, for the area of pi r squared, the value of the flux that will be produced, okay, will be pi r squared over pi a squared, right? For the area of pi r squared, the value of the area will going to be pi r squared over pi a squared if you want to make the proportion, right? So therefore from here, okay, I will try to make it slowly, yeah, from here. Our H will then be right, so therefore for the area of pi r squared, what we need to do is, okay, the flux internal for the area of pi r squared, yeah, for the pi r squared area, okay, so it is a proportionate, so we need to add at the front part, yeah, we need to add the front part, the proportion area, okay, so from 0 until a, so mu naught IR over 2 pi a squared, okay, so from phi direction, okay, so our ds also going to be on phi directions, so it will be, instead of integration, so let me write on this part, we're going to be on dr dz, okay, phi direction, so dr dz also we're going to be on the phi directions. So if you solve this, you will be able to get the value of for the internal flux, yeah, will be equals to mu naught I over 8 pi, okay, mu naught I over 8 pi L, right? Mu naught pi over okay, oh, I think this part there is no L at the downside, yeah, this L should be up, yeah, okay, this L should be up, yeah. For the pi a squared area, the value of the internal flux we're gonna be mu naught I L over 4 pi, right? Whereas for the area of pi r squared, it will gonna be mu naught I L over 8 pi, right? So just now we already get at the internal side the value of the flux for the area of pi r squared at the regions of r lesser than a. Okay, at the regions of r lesser than a, we are able to get the value is mu naught I over 8 pi L. Alright, and therefore we can find the inductance for the internal side. Okay, it will gonna be inductance per meter, right? So flux over I, so it's gonna be mu naught 8 pi L. So since that they asked about inductance per meter, so this L we should bring downside of here, downside of here. So it's gonna be L internal over the length, so it's gonna be mu naught over 8 pi. So this is the value Henry per meter. Yeah. So this is the value of the inductance that is produced inside the conductor 1 at the regions of R lesser than A. Okay, R lesser than A. By using the methods of, we are using the first method, right? We are using the first method where we find the value of flux amount. Okay, we find the value of the flux amount first. Okay, so there is another method that we can use. As I mentioned earlier, we can also use the second method where we can use by using the energy density. Okay, energy density. So now let's look for the second method by using the energy density. Okay, so energy density can be determined by using the integrations of B dot H dV over equals to Li squared, right? So from here, the L internal, okay, we can straight away get the L at the internal side is equals to the integrations of B dot H dV over I squared. So B and H is the one that we have calculated earlier. Okay, so we can straight away put inside that. Okay, which gonna be mu naught over 4 pi squared A for 0 until A, the limit for us cubic dr, 0 until 2 pi, the limit for phi, and 0 until L, the limit for dz. Okay, and from here, of course, you can get straight away that L internal over L is equals to mu naught over 8 pi. Okay, mu naught over 8 pi Henry per meter. So you can compare if you are using with different method as well, you will get the same answer. Alright, but the key is you need to calculate both method. You need to calculate the value of B and the value of H. Right, so B is equals to mu naught H. So the key is you need to get the value of H correctly so that you are able to solve the questions. Yeah. Okay, so that is for the regions of R lesser than A. How about at the regions of A? How about at the regions of A, R, D minus A at the external part? So at the external part, of course, we need to find the H first. Okay, if we are using the first method. Okay, if we are using the first method, we need to find, by using the flux linkage, by calculate the flux. Okay, so we need to find the H. H can be determined same as before. The I enclosed are going to be I, the total I that is inside that structure are going to be I. So we are able to get the value of H is equals to I over 2 pi R. 2 pi R, 2 pi r on phi direction. Okay, and from there we can find the flux by using B dot ds. Okay, and from here we will get the value of the flux is equals to mu naught I over 2 pi, okay, ln d minus a over a. So I leave it to you guys to prove this, yeah, to prove this. Okay, d minus a over a ln d minus a over a, and l will gonna be the length, yeah. So the L for the external is equals to psi m over I. Okay, so equals to mu naught over 2 pi ln d minus a over a L, the length. So we want to find the external per meter, inductance per meter. So over L, so you will get for the external part 2 pi ln d minus a over a, right? So this at the regions of a, between a until d minus a. Okay, so this is by using the first method. So let's use the alternative method, second method, by using the energy density. So it's gonna be half there's no half here. B integrations of B H dV equals to Li, right? Equals to Li squared. Okay, so the B is equals same as before, so we will get mu naught I squared over 4 pi ln d minus a over a L is equals to Li, right? Li squared. So to get that, okay, we will get the L for the external is equals to mu naught there's no more I, eh? The I squared can be cancelled to each side, this side and this side, so it will left behind 4 pi ln d minus a over a L, right? So L external per meter is equals to mu naught 4 pi ln d minus a over a. Alright, so to get the total, so total L we're going to be internal plus with external. Okay, so we will get the total inductance that is produced. Okay, L we're going to be mu naught 8 pi plus mu naught over 2 pi ln d minus a over a. Okay, so this is the value of total inductance that is produced at conductor 1, only at this conductor 1, yeah, at this conductor, only at this conductor. How about at this conductor? How we want to find at this conductor? Okay, for this conductor, if you look, okay, you can go to the same process as well, okay, but to make it shorten, if we look at the center part here, how is the directions of the H field? The directions of the H field, both of them is on the same direction, right? It's going this direction. So therefore, to make it shorten, therefore this total inductance that is produced at conductor number 1, you just need to multiply with 2. Because of what? Because at this part, the directions of the H field is same. Okay, let's say if the direction is vice versa, it's going like this way. So what you need to do, it is cancelling each other. Yeah, it is cancelling each other, so it is equals to 0. Okay, right? So so that is the simplest, I mean the shortest cut, the shortest way, so you don't have to calculate 2 times. Okay, but you have to make sure that the value of I that is produced inside here, okay, the value of I is same. Okay, so in that case, the H field at this part, at the center part here, we're gonna be plus together. Yeah, plus together, so you just need to multiply the value of the inductance. Yeah, if the case is if the case is semiconductor, so okay, semiconductor usually it gonna be a different direction, so therefore the value of inductance is equals to 0. Okay, right? I think that's all. Thank you so much.